Size because the flu season is coming. Want to be strong. So tutorial 4, you probably haven't started yet. I have to run through all the 3 problems today because it's still Friday and no class on Wednesday for the career fire. So the first one I want to talk about is this. So everything about tutorial 4 is trying to teach you node voltage method. So when you are doing node voltage method, you use KCL. Okay, let's see. VS is let's just assume this is VS, right? VS. And 8K ohms, 5K ohms, plus or minus VO, 1K ohms, 3K ohms, 2K ohms, IS. So I'm not asking specific questions regarding like the power consumption for one component. If these 2 sources are given, you are able to solve the circuit. So when I'm saying solving the circuit, it's basically solving all the voltage nodes and currents for each component. So you should be able to know everything about the circuit. Okay? So where to start with? Before we run into the details, you should know a node and an essential node. Just concepts, okay? Essential node. So essential node is had at least 3 branches, and this is at least 2 branches connect to the node. For example, this one is an essential node because it has 3 branches connect to it. Essential node, essential node, essential node, essential node, right? Just a concept. Right? So how many essential nodes in this circuit? 1, 2, 3, 4. Right? 1, 2, 3, 4. Okay, if we label the voltages as follows: V1, V2, V3. Remember, node voltage method is asking to use KCL, even though you label these nodes as V1, V2, V3, but you are basically using KCL. Okay? So now let's list all the equations for the currents. Let's look at V1. Where's this node? What are the currents getting into the node? You got IS, right? IS. So I think there are values for it. So IS is 10 milliamps, and VS is 120 volts. Okay. So definitely currents, right? Currents. So IS, which is 10 milliamps, equals what? This current plus this current. So this current, because the voltage of the nodes are given, so you can use this voltage minus this voltage to get the voltage difference across the resistors, and divided by the resistance, you get a current. That's everything about node voltage method. Do you get that? You have the nodes, right? Sometimes they are not given, sometimes they are given, doesn't matter. If it's not given, you just put a variable there. Okay, and then use this node minus this node, you can get a branch current. And then apply KCL. KCL is Kirchhoff current law, right? So all the currents flowing into the node is 0. The summation of all the current flowing into the node is 0. Or the current flowing into the node equals the current flowing out from the node. Now we are using the current flowing into the node, which is IS, 10 milliamps, equals the currents flowing out from the node, which are these 2 currents. Okay, so calculate this current, you need the voltage across it and then divided by this resistor, which is V1 minus V3 over 5K. And now let's look into this one. This is V1 minus V2 over 1K. That's the first equation you can get, right? What about this node? Current. Okay, so V1 minus V2 over V1 minus V2 over 1K plus V3 minus V2 over 8K equals, we ground it, so it's basically just the V2. V2 as this node will be the voltage across this 3K ohm resistor. Same thing. This is 0 volts. V2 minus 0 is still V2, right? So the voltage as this node will be the voltage across this resistor. So another question, is the voltage across this resistor V2? No. V2 is just the voltage as this node. Sometimes people are getting confused because I labeled V2 and this V2 becomes the voltage across it. And also I labeled V2, but the voltage here is not a voltage across this guy. Why? Why it's different?
The voltage across that is the drop from 3 to 2.
Yeah, because this is from 2 to 3 and this is from 2 to 0. This is shorted to 0, this is not. That's why V2 is the voltage that's node, but also the voltage across this resistor, because this is grounded. But this is not. If you want to find out the voltage across this guy, you have to use V2 minus V3, right? So now we are having trying to calculate the current flowing from right to left, so we have to use V3 minus V2, right? V3 minus V2 is over 8K will be the current flowing into the node, and 2 going into the node and 1 coming out. So we are using V2 over 3K. That's the second equation. So I have V1, V2, V3, three variables. You need the 3 equations. And now we have 2, right? So we need another one. And you can definitely use this one, this node, to list all the currents for sure. So here's 1, 2, 3. Okay? Now, let's see. What is the current here? How do we find the current here? It's not that straightforward, right? You got a voltage source and messing things up. It's not directly just the 2 voltages on one resistor can directly use Ohm's law to do it. But how do we deal with this guy? How do we get a current? Just tell me.
Voltage over resistance.
Over, yeah, well, how can we find the voltage across it?
You know that
We know the voltage here, do we?
yeah.
Yeah, it's 0, right? Do we know the voltage here? Not yet, but can we calculate it?
Oh, we use a relative one.
Use what?
So we need relative conformance.
Yeah, it's relative. So we already assume the voltage at this node is V3, right? And this battery is going to drop it by what? By 120 volts. So what's the voltage here, though? Yeah. So now we got a voltage across it, right? And then we can calculate the current. So this one, we got this current first, which is V3 minus 120, which is the voltage here, right? But however, the current is flowing up. We assume it's flowing up. It's pointing up. So what should we do? Plus minus, right? Because it's flowing to the left, to the right. So which minus which? This is here. This is 0. And I already know the voltages across it. So which subtract which to get a current, and over this K, 2K, get a current flowing to the right. Definitely from left to right, right? Because it's pointing to the right. So that's why I want to use 0 minus this guy and divide it by 2K to get a current flowing up. And then this one is V3, so 1 going in and 2 going out. So this equals V3 here minus V2 over 8K. You get a current here, and you want to get a current here, which is V3 minus V1 over what? 5K. Okay, 3 variables, 3 equations. You should be able to solve it. Solve everything here. So get the voltages, and let's see the questions. What's it asking? Find the current leaving the node through the current source. The current leaving the node. Find the current leaving the node through the current source. Oh, okay. So the current leaving the node through the current source, which is basically the current of this guy, right? So the current leaving the node through this current source. Here's the node of the current source, and leaving. The current leaving will be the current getting into it, right? Same thing, KCL, same stuff. The solution has a minus sign in front of it. So it's assuming this is a positive. I think you have to calculate this. So leaving to where? Like going here is leaving or going here is leaving? I think going here is leaving, right? So you have to calculate the voltages and find out the real currents. It should be leaving because the current leaving this node should be positive actually, but the solution is a negative value here. Anyway, so it should be 10 microamps, 10 milliamps. The reason is this because this current source is given. It's 10 milliamps. We have to trust it. It's going to be 10 milliamps. Okay, so if this is 10 milliamps for sure, and the current of these two, you add them together, they must be 10 milliamps, right? Okay. If you put a positive number there, you got a wrong answer. Just put a negative sign in front of it. Yeah. Okay. So if you can calculate the voltages over here, here, and here, you should be able to calculate everything. I agree with that. Any questions for this problem before moving to the next one? We have 3 problems to cover this today because that's everything about tutorial 4, I think. Just the 3 problems. Oh, there's another one. Started more than that. That's crazy. That's crazy. Let's keep moving, okay? Don't have time. Running out of time. Sorry, guys. This is bonus points anyway. Due Friday. So much. Let's do another one because it's recorded, so you can always come back, right? So I don't want to waste time during the lecture. Let's keep moving. For 50 milliamps, 100 ohms, 5 ohms, 25 ohms, 45 volts, 6.25 I delta. So where's I delta? This is I delta. Yeah, that's it. All right. So using node voltage method for a circuit with the dependent source. No difference, okay? No difference. Given current, just assume a bunch of currents. I1, I2, I3. Okay, then started writing. 45 milliamps equals I1 plus I2, no problem. 1 getting in, 2 going out. All right. This one, you got I delta and I3, I2, I delta, I3. So I2 plus I delta equals I3. Okay. Anything else? 1, 2, 3, 4. So 4 variables, we need 4 equations. So what is I delta? I will assume another another voltage. It's okay because we don't have that many voltage nodes. If we ground here, let's just Vx. Don't be afraid of that. Adding more variables is okay. What's the voltage here? 45 volts. How we can know that? Because this is grounded. Nothing else in the middle, right? Definitely 45 volts. Can we find I delta? Yes. I delta is what? 45 minus Vx over 25. What is I3? I3 is Vx minus this, because this is the voltage. It's boosting 0 to here by this much. So the voltage here is this much. It's a current control voltage source. So the voltage here is this. And we know Vx. It's assumed. It's a Vx. So I3 is Vx minus this guy, 6.25 I delta over 5 ohms. So again, I3. I1, yes, Vx here, Vx here. What is I1? Vx over 100. This is 0, right? So 0, Vx minus 0 over 100. How many variables? I1, I2, I3, I delta, 4. Plus Vx, 5. 1, 2, 3, 4, 5. Done. Okay? All right? Another one. Two voltage sources, V1 and V2, and 8 volts and 17 volts. This is the easier one. I mean, you got 2 sources, you got several passive components, you can solve it for sure. Just a bunch of resistors. Everything is confirmed, no changes. You know what they are. How many essential nodes do we have? I mean, this is ground. So don't include this guy. 3, right? 1, 2, 3. Right? Ground is just ground, just one ground. I mean, you're saying, oh, 3 nodes. I have to calculate 3 voltages. Is that correct? Do you have to calculate 3 voltages? Why?
Because you know what the voltage is on the other side of the tube.
Yeah, it's given. It's given. So simple. All right. Just assume 1 Vx here. Vx. Just to list 1 probably. Just list 1. KCL. 8 minus Vx over 25 is this current. Plus 17 minus Vx over 140, which is Vx over 10. Then Vx is calculated. It shouldn't be in tutorial 4. It should be in tutorial 1 actually. Anyway, done. Done. Everything's done. Any questions? Good? Okay, cool. The last one for the first half of tutorial 4, then we move to the second half. Oh, is there a... There's another one. Let's see. Simple enough. Yeah, let's move to the next one because this is the last one is very simple for the tutorial 4. See how much tutorial 4 is? 42 pages. You haven't started yet, right? Have you started? No? Just let you know, heads up. So for the first 22 pages, just the 3 problems. And I already covered it. So it shouldn't be that bad. For the next one, oh, another one. So we just covered node voltage method. For the there are 3 main methods to solve circuits. So node voltage method usually the first one. You guys are going to learn, and the second one is called mesh. Current method, which uses KVL, and this is really useful. Both are very useful, but this is more, it's actually easier math-wise. $4K, $2K, $8K, and $9I alpha. Here's I alpha. $5K. Yeah, that's it. 200 volts. All right. It's asking for how to write the KCL equation. So it's labeled Vx, Vy, and Vz. KCL. Remember KCL? You go through the loop, add all the voltages is equals 0. So how do you write KCL? Okay, because these voltages are already labeled, right? But KCL is a current equation. Yeah, KCL is simple, right? So KCL is just gonna be the V's, Vy minus Vx, for example. Here, Vy minus Vy over this guy, which is this. Vy minus Vz is this. So according to whatever we just did, the node voltage method, okay, you have all these voltages labeled. You can definitely write the KCL equation for this node, right? No problem. For node Vy, right? So just Vy minus Vx over 4K. So this time we have all the currents pointing out, flowing out from the node. So we basically just add them together. This should be 0 instead of like we put the current going in on the left and the current going out from to the right of the equation, and they equal to each other. So now we just add them together. They equal to 0. It's the same thing for KCL. So Vy minus Vx over 4K, which is the current flowing out in this direction, plus here, which is Vy minus Vz over 2K, and plus Vy minus 0 over 8K equals 0. That's a KCL equation. So this is not the important one. So the important one is mesh. Mesh. It's one of the magical methods you want to use to simplify the solving the circuits. Oh, missed the one resistor. 2K, V2, 1K, 5K, 8K, V1. So the mesh current is the current you assume in the mesh, because these are 2 meshes. mean, it's like a mesh, right? So you assume the current flowing into the mesh here as I1. Usually I use clockwise current, I2. So if you assume the current flowing in this mesh is I1, because you don't have another circuit here sharing this node, sharing this component, so I1 will be the physical I1 flowing into through this component. Same to this guy. However, if you look at the one shared by these two different circuits, the current flows through this resistor would not be either I1 or I2. So what that would be? Again, so when you are dealing with mesh current method, keep in mind, it's not something like we label it, we know it's exactly physically flowing through that single resistor. This is like a semi-virtual current. You know what I mean? So eventually it works. When we move down the road, you will figure out why. But now just remember the procedure here, and that's the method you want to know how to use, right? So we assume here's a current flowing clockwise, another current flowing clockwise here, and because these components not being shared by another circuit, so this current will be real. This current I1 will be the real physical current flows through this resistor. However, this one's different because it has two current, right? So I1 flowing down and I2 come back flowing up. So it's a combination of these two currents for the physical current flows through this 5K. So that's why I call it actually a virtual current. So I1 flowing down, I2 flowing up. So I2 is trying to cancel I1 from top to bottom. So if you assume the overall current, like the overall current, effective current flows through 5K from top to bottom, you have to use which minus which? I1 minus I2. Does that make sense? And this is the real physical current flows through it. But eventually you calculate, you list all the equations, KVLs, you calculated I1 and I2, then you know I1 is the physical I1 here, is the physical I1 here. However, I1 is not the real current flows through this 5K. You have to use I1 minus I2 to find the real current. That's how you do it. Okay? Now let's start from here. KVL. Start traveling from the bottom left. Okay? So what's the first voltage you see? If it's a minus, you put a minus sign in front of the voltage. What's the first one you'll see? Minus V1, right? Keep traveling. What is this one? I1 flowing from left to right. Okay? So it's causing a voltage drop from left to right. It's plus. So it's plus I1 times AK. That's the voltage here. KVL. Okay? And then going down here, plus, because that's I1 is from top to bottom. No, the overall I is from top to bottom. We are using I1 minus I2. That's the overall current from top to bottom. So it's causing a drop from top to bottom times 5K. And that's equals 0 because that's KVL. You add all the voltage in the loop, eventually you get a 0. Same for this one. You have a little guy here, start traveling. Okay? Which one to start with? So now you are looking that direction, right? So let's use I2. So now I2 is dominating. Or we are looking at the overall current flowing up, right? Flowing up. So we use I2 minus I1. I2 is going up, I1 is going down. So the overall current flowing up is I2 minus I1. Times what? 5K. Plus I2 times 1K. And here it's a minus plus, so it's minus V2. Alright, because this is I2 going here, flowing through 2K. So it's plus I2 times 2K equals 0. Because sometimes if the circuit scales up, the number of equations increase significantly sometimes. So you want to list all the equations and use the matrix solver to solve for the answers. I'm going to show you how to do it here. We have, since V1, V2 are constants, so we basically only have two match currents. So there will be only two elements, 2x2 matrix. This one is easy to solve because only two equations. I know it's boring. You know, you guys are getting bored. Circuit 1 is like that. A lot of algebra. But you find out two i's, two variables, and two equations. You can definitely solve for I1 and I2, okay? So we'll move forward with the more complex problems. I'm going to show you how to use the matrix solver to solve for the voltage and currents in it. Okay, one more question. If you so use these two equations, you can calculate for I1 and I2, right? No problem. So get I1, I2, can you get everything in the circuit? Yes, because I1 is given, and I1 minus I2 will be the real physical current flowing from top to bottom for this resistor. So you get a voltage. You got a voltage, done. You know everything about the circuit. Let's move to the next. Okay, keep moving. Oh, it actually, the tutorial shows you that 2x2 matrix. Let's do it. So V1, let's see, what's the V1 and V2s? What are V1 and V2s? 25. V2 is 39. Okay. Combine all the I1s and then I2s and put a constant to the right side of the equation. So now you got a 8K, 5K, so eventually it's I1 times 13K. I2 is minus I2 times 5K equals minus 25. Move to the right will be 25. That's the first one. And second one, you got I1, and that's the only I1, so it's minus I1, 5K. I2, you have 5K I2, 1K I2, and 2K I2, right? So eventually it's 8K. And V2 move to the right will be 39. Okay. I've taken linear algebra. You? No? Some? Okay. It's okay because I took it in undergrad, but I forgot everything already. I only remember this because I'm teaching circuit 1. That's alright. A matrix. What is a matrix? Matrix is just a collection of numbers, right? Nothing else. No magic. So you can take out the elements here, 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 okay, and put in the matrix. It's just a big bracket. The coefficient 13K minus 5K minus 5K. Take the sign with it, okay, and AK. Matrix multiplication, I1, I2. I'm going to show you how to do it. So if I write it down this way, this is the same as whatever on the left hand side of the equation, and this equals what? Equals this. It's a column matrix. 25. It's a vector actually. That's it. So this can be rewritten in this way. Why we want to use matrix? Have you asked this question to yourself when you learn linear algebra? I mean, linear algebra, they just write down all the matrix on the board and teach you how to solve for that. It never tells you why, right? So there are a lot of applications. I mean, in computer science, in math, physics, in a lot of places. However, for computer engineering, electrical engineering, especially for computer vision, it's quite interesting actually. So look at the camera of the phone. So what's happening inside or behind the lens is actually a matrix of pixels. So the chip is called CMOS imagers. Okay, it's a relatively bigger integrated circuits, because it's taking an image. So compared to other like memory chips and CPUs, the area is a little bit bigger. The footprint is a little bit bigger. So it has like millions of pixels. Okay. So every pixel, it's getting complicated. It's called a TIA. It's called RF. That's VL. So this is the amplifier, and this is a photodiode. So when a photon hits that photodiode, it generates a photocurrent and flowing that way. Very interesting, right? So Einstein found that and won a Nobel Prize 100 years ago, photo effect. So whenever a photon hits that semiconductor material, it generates a photocurrent flowing through that material, and depending on the intensity of the photon or number of photons, it generates a different amount of current flowing through the circuit. So what's happening is the current is going to flow through that RF, which is usually like 1 mega or 1 mega ohms, thing like that, because this current is tiny. It's just a photon being generated by current being generated by the photon, or like one single photon sometimes. So it's like this is like femtoamps level, or even lower, I think. And it's so when current flows through a resistor, what happens? Voltage, right? So it's converting that photocurrent into a voltage. That's something start fascinating, because a little photon, okay, photon comes in, voltage comes out. Okay, you get a strong photon, get a strong voltage, because all the ADCs we have, the analog to digital converters we have, are converting voltages. So if you get this photon converted to voltage, and you use this little device called ADC to convert that analog voltage into a digital voltage, you can store that digital signal into the memory, so you can process it. So every single pixel will give a certain voltage level, analog voltage, that can store as a digital voltage in the memory. And that's how you can get all the images. So that's just one pixel. If you have like 1 million by 1 million pixels, so every single pixel will form a little data, and eventually you get a picture. So this is the matrix. This is the matrix. It's a matrix of data, and the data are the photon intensities actually storing in the memory. So that's one of the applications for matrix. This is just 2 by 2, but you have 1 million by 1 million. You get a matrix of data, and you can process it using all these signal processing equations. That's another course, okay? But now you can tell matrix are being used in many different places. This is one of the examples. So if you have these linear equations, and you can convert it into this format, because the computer likes this format. They are just numbers. You put in the numbers into the computer. It's just like MATLAB, right? You type it in, and MATLAB will be able to calculate this easily for you, and eventually find out I1, I2, because you're calculating for I1, I2 here. Okay. Now let's see how we do it. So there's a matrix called inverse matrix. Inverse matrix, and you can directly calculate it. Okay, I'm going to show you how to do it. Let me write down the equation first. So inverse matrix. So for example, this is A. So this matrix is matrix A, right? And this is matrix B. Okay. So what's happening is you have A times I1, the two variables, the variable matrix, and getting you matrix B. Okay. So in linear algebra, what you can do is times the inverse of matrix on both sides of the equation. Nothing will be on this for linear algebra in this class. Okay, don't get scared. You times the inverse matrix on both sides of the equation. It has to be on the left-hand side. It doesn't like numbers, right? It has to be on the left-hand side of this whatever already exists. Okay? And you combine these, will give you a 1. It's called a diagonal matrix. So this one times this is still this. Variable matrix, still the same thing. So that's why you want to times the inverse matrix on both sides, because you can cancel out A and eventually have only variable matrix on the left hand side. So this equals this times this, right? So which is A inverse, which is this guy's inverse matrix, times this one, now which you can use a calculator to do it. So let's try it really quick. I have 6 minutes. It should be enough amount of time to do it. And I have, there are some other, like it's just mesh. Okay? So for the rest of the tutorial 4, just the mesh method. If you look at it, just apply the same theory like what I did for the 2 meshes. You have 3, it should be the same method. But now I want to show you how to do the matrix calculation, so you will be able to calculate it. Alright, go to my website. Matrix solver is ready for you guys to use. Okay, 2 by 2, right? 2 by 2. What are the numbers? Let's see. 13K. 13K. And this is minus 5K. And this is minus 5K. And this is 8K. Okay? Matrix A. And inverse times matrix B. So matrix B is 2 by 1. It's 2 row and 1 column, which is 25 and 39. Okay? So we have to do inverse of matrix A first. So that's inverse of matrix A. You don't need to calculate it. I just use the calculator, okay? And copy to A. So it's going to replace everything here. So what you are getting is this. So inverse of A getting replaced. And now here's B. B I already typed in. Here's B. And 8 times B, right? Done. So what are these two values? Is 0.005 and 0.008. If you come back to the paper, and the nice thing is, this will be I1 and this will be I2. Just follow this procedure to calculate all these variables in the linear equations using inverse matrix and the link on my website. And even there are like four meshes, 4 equations, 4 variables, you can still solve for that. No problem. Any question on anything? No? We still have 3 minutes. I'm gonna, because there's only one problem left, basically, even though there are like 20 pages. But only one problem actually. It's very simple. Let me just draw the mesh for you really quick. I'm going to show you how to do it, okay? milliamps. Assume 1 mesh, and this is 3K, this is 1K, 5K, this is 2 V delta, plus minus. Assume I1, I2, I3. Okay? And sometimes you have a current source. It's difficult to find a voltage because you cannot use the current times the resistor to get a voltage, and it's not a voltage source as well. In that case, just assume a Vx over here. If this guy's a Vx, it's plus minus Vx, right? So if you have someone start traveling, it's gonna see minus first. So whatever across this guy will be minus Vx, starting from minus. Okay, and there's no voltage. But here is the voltage, which is I1 minus I2, because I going down, 2 going up, I1 minus I2 times 3K. Done, that's it for the first one. And second one, starting from here as well. You don't have to draw a little guy here all the time, but just showing you. So I2 minus I1, right? Times 3K will be the voltage here. Going to the left, to the right will be I2 times 1K. Here will be I2 and I3, right? Plus I2 minus I3 times 5K equals 0. That's it for this one. Here, I3 minus I2 times 5K will be the voltage here from bottom to top. And then going down here, giving you plus 2V delta equals 0. Now I have more variables, Vx and V delta. So V delta is the voltage here, it's given. So V delta is I2 times 1K. Here's I2. It's not shared with any other circuits. So it's going to be I2 flowing through it. Okay? I1 given. I1 is 50 milliamps. Nothing sharing. So I1, virtual I1 will be the I1 here. Will be the I here. Done. 1. So I1, I2, I3, 3 variables. Vx, V delta. 5 variables, 5 equations. Okay? Should be good for tutorial 4, and we'll cover homework from Friday. Okay?